chemical kinetics. So, what's the first thing that comes to mind when you hear the word kinetics? Well, if you've been in the sciences for a while, kinetics means motion. You may recall kinetic energy. Kinetic energy is something that an object possesses as energy due exclusively to its motion. And it's chemical kinetics is kind of like that, except that it's motion in terms of the mathematics of the term, which is a change over a certain period of time. So time is an issue, but it's not necessarily physical motion. Of course, with any chemical reaction, you've got physical motion, you just can't see it. Usually it's microscopic. All right, so when we talk about chemical kinetics, and if you've looked at if you're curious enough to look at the chapters that are coming down the line, you'll notice that kinetics comes before equilibrium. And for good reason. Equilibrium is an expression of kinetics as a balancing act. So you have a reaction rate that goes one direction, the products, and we're going to talk about that today. What's the rate here? The change that takes place over time. But when you get to equilibrium, you're concerned also with the reverse reaction, and it has its rate. And for equilibrium to exist, the forward rate has to balance the backwards rate, the reverse rate. So that's why we're covering reaction rates, the kinetics first. Okay. So we need a way to express the rate of the reaction. And we're going to start off sort of generically. We're just going to say rate is equal to something. And usually we're concerned with a change in concentration of, in this case, A. How does it change over time? So you have a final concentration minus an initial concentration over an interval of time. So the ending time minus the beginning time, right? And that's the way change is always expressed. It's the end value minus the beginning value. And of course, here they say T2, concentration at T2, T2 minus T1. But what they really mean is final minus initial. And then we express that as a delta. So delta just means a change, right? So if you were to look at a plot of a straight line, you would see right, some here, maybe that straight line. The slope of that line would be the change of y over the change of x. Right? So the slope is equal to delta y over delta x. Okay? That's a preview of what's coming, because this could very well be and is also represented as a slope of a line. Change in A over change in T. So A would be here and T would be here. Okay. We typically express concentrations in terms of moles per liter, of molarity. But if the reaction involves only gases, sometimes it's more convenient to express the concentration in terms of partial pressure. So the partial pressure of one gas under these conditions changes over time. And if A is a gas and it disappears over time, then the partial pressure should go down. Right? But in the beginning, we're gonna talk about concentration in terms of molarity, because molarity covers everything. You can express anything in terms of molarity, but only gases can be expressed in terms of partial pressure. So that's reaction rate. Some change over time. Here's a data set. I pulled it straight out of the textbook. Table 12.1, the first table in the chapter. And it's referencing this balanced equation, right? 2 moles of nitrogen dioxide gas. Oh, look, all of these are gases, but we're still going to talk about them in terms of moles per liter. And that yields 2 moles of nitrogen monoxide plus 1 mole of oxygen, right? And this is a balanced equation. So in the beginning, you'll notice at time 0, the concentration of nitrogen dioxide is 0.01 molar, which is reasonable, right? If it's so many moles per liter, gas is pretty thin. So in a liter, you don't have much. But we're starting off with 0.01 molar nitrogen dioxide, and there's no nitrogen monoxide and no oxygen because the reaction hadn't started yet. Now, there are a number of ways to secure that. Temperature is one of them, right? You just keep it cold enough and no reaction takes place. And then you increase the temperature really quickly to 300 degrees and start your timer. And somehow you measure it. Don't ask me how. If you're going to measure on 50-second intervals, it's probably spectroscopic. You're going to shine a light through it and measure a certain wavelength of light out the other side. Anyway, notice what happens. Over time, you get a decrease in the NO2, right? And consequently, you get an increase in the NO and the oxygen. But look at the ratios, right? How much does this one, the change from here to here? Well, if you subtract 0.0079 from 0.01, the difference is 0.0021. Right? So that represents 2 moles of NO2 is 0.0021 in that stoichiometry. So since there are 2 moles of NO for every 2 moles of NO2, that 0.0021 concentration shows up as NO. Okay, it's a 1-to-1 relationship, a 2-to-2 relationship. But look at the oxygen. What's the ratio there? The ratio there is for every 2 nitrogen dioxides, you get 1 oxygen. So the value here in the first time interval is half of that value. Okay, so the stoichiometry is still there as the reaction proceeds. And you'll notice as you change, right, you get that same ratio. Until the end of the reaction, whatever that happens to be. Sometimes it's dictated by the reaction. Sometimes you just choose, when to stop observing. Particularly if it's a long-term reaction. If it takes days and weeks to accomplish, then you just have to call it quits after a while. But there's another reason. And it alludes to this reverse reaction, right? Once you start getting substantial amounts of products, then you run the risk of competing the forward reaction with the reverse reaction. Then you can't tell with the measurements you make which one's which. You know, which one are you measuring? So we usually study these reactions. One way to study them, I should say, is initial rates. What is the rate of the reaction at the very beginning? Say the disappearance of a reactant when the concentration of the products is so low that the reverse reaction can be ignored. So that's one way around that problem of competing reverse reaction. And we'll talk about that in a few minutes. But that's what a data set would look like. Okay. So this is what it would graph out to be, right? Concentration on the y-axis, time on the x-axis, and this green line is NO2. So you start off with this much NO2 and 0 products. And they gradually increase, right? So the NO curve is just a mirror image of the NO2 curve because of the stoichiometry. It's a 2-to-2 relationship or a 1-to-1. So as this appears, this disappears at exactly the same rate. Whereas the appearance of oxygen is exactly half that. Okay? Now, how do you find the slope of a curved line? It's kind of hard to do. It's not straight, right? So it depends on what point of the line you're on. The 2 points that you choose on the line will give you, let me annotate that. I want to illustrate this point. I need a straight line. Okay, here we go. So if we were to choose these 2 points right here, one, and now let's go down to this one and use that one, right? So the difference between this one, between here, let's use a different color. If we were to choose this one for our y, right, from there to there, and from here to here, right? Okay, so that would be our y difference, concentration. And our x difference would be, say, from here to here. And from here to here. Right? So you would get a y value over here for your concentration divided by your x value difference over here. Well, notice that that straight line sort of takes a shortcut, right? Going from this point, let's see, going from this point here to this point here is a shortcut. So it's really not the true slope of that curve. It's sort of it's an estimate. And the flatter the curve, the better the estimate. But if it's a very curved line, I mean, it's serious curve, then you're losing a lot of information by doing that type of analysis, measuring the slope. So what we do is we use a mathematical technique, a geometric technique of tangent. What is the tangent to the curve? Right, so there's a lot of mess in here, so let me get rid of that stuff. Let me erase it. There we go. Okay, so now what we have is the tangent, which is shown here in a very narrow line right there with the dotted lines here and the dotted lines there, right? So that, the slope of that tangent line is the true slope of this curve at that instant, that point. We call it the instantaneous slope of the line. And notice that depending on where you measure that tangent, the slope of that line changes. So up here, it's very steep, right? Down here, when it starts to shallow out, the slope decreases. But at any one point on that line, you have that capability to calculate the slope. Now, in mathematical terms, calculus, that's called the derivative at that point. So it's easy to calculate. Okay. So this instantaneous slope or instantaneous rate is characteristic of that reaction at that point. All right. So, and you know how scientists hate curves, right? We have to deal with them, of course, but whenever we can get a straight line out of it, we go for it. If you can't make the whole curve a straight line, take an instant of time and make a straight line there. So that's what we've done with that instantaneous rate. Well, the rate law can be expressed for any reaction in terms of any of its reactants or products. See? In this case, we're expressing the rate law in terms of the reactant, a disappearance of a reactant. We could just as easily express that rate law in terms of the appearance of a product. But for simplicity's sake, we're going to discuss most of what we have to say from now on in terms of the disappearance of a reactant. For one reason, our instrumentation may only be able to detect a certain amount of a product. So if you start off at 0 and then you get just a tiny amount of your product, your instruments may not be able to detect it at that concentration. And then where would you be, right? Well, you'd lose the first part of your reaction. So that's one of the reasons we go for disappearance of product, because there's a lot of it usually, measurable amounts of product. And then you can measure the disappearance of that more easily than you can the appearance of a product. The disappearance of a reactant is easier to measure. So what does the rate law look like? Well, for this reaction, the rate law would be just the rate equals some constant. And that is a constant for the reaction. And then the concentration of A. Right, what is the concentration of A when you start, or at any point in the reaction? What is its concentration? And you raise that to a power. And that power is called the order. In this case, it's the order of the reactant, because there's only one reactant, right? So the order of the reaction overall is also that value. So if it were 1, the order n equals 1, the order would be 1, or it could be 2, second power, it could be 3, third power. And if there's only one reactant, then the overall order is the same. But that's the general format for the rate law. Now, if you have more than one reactant out here, say you had 2 reactants, say we had a B reactant out there, then you would have another term in the rate law with its own order. Right? It would be whatever power that is. And orders can be 0 also. In fact, we're going to look at 3 most common reaction orders, 0, 1, and 2. So that's the order of that reactant. Let's see. There we go. So this is just a statement that we try to study reaction under conditions where the reverse reaction does not contribute to the overall rate. Now, we study them both ways. Don't get me wrong. We study them at initial rates and we study the entire reaction. So you have those 2 possible data sets to use to describe your reaction. You can never have too much information in the sciences. You can always throw it out for valid reasons, of course, but you can never create it. You're not supposed to create data. That's called fraudulent research, if you create data. But if you have a lot of data and you need to throw some of it out, then that may be fraudulent. But if you have valid reason then and can justify it, then it's not fraudulent. Now, another characteristic of these orders, these numbers, powers, is they have to be determined experimentally, at least in the beginning. You cannot take the balanced equation and derive from the balanced equation the value of that power, that order, right? It's completely independent. If they happen to be, say, a coefficient of nitrogen dioxide in our previous reaction is 2, the coefficient is 2. If the order of that happens to be 2, it's coincidental. At least until I show you something else. Okay. It's called mechanisms. When we get to mechanisms, then I'll show you how they're related. But right now, the order has to be experimentally determined, and should be a whole number. If it's not a whole number, let's see, I wrote it down here. If it's not a whole number, it's called a broken order or a mixed order reaction, which means you're not really getting at the reaction you think you are. Right? And that's entirely possible. And when you do the lab for our chemical kinetics, you may end up with one of the orders being not a whole number. And that's okay, because I'm more interested in your ability to tease out those values rather than shoehorn them into whole numbers just to satisfy conditions. Now, you can do that when you write your report. You can say, I think it's close enough to this whole number, it should be that value. But you have to work from a real determined value, which may be a fraction, before you get to the whole number. All right, that's another topic. It's just a word of caution. You cannot derive the order of a reactant from the balanced equation, not legally. Okay, so there are basically 2 types of laws, expressions. The differential rate law shows how the rate of the reaction depends on the concentration. Right here, rate depends on concentration. Right, so if the concentration starts here with its order, and you have determined the rate constant, then you can calculate the rate of the reaction for that concentration. Okay, but notice the rate here, the time factor, the actual measurement of the time is buried in this term right here. Right? Sometimes you want to know what's the time. You know, how long does it take the reaction to go from this concentration to that concentration? Well, we have an integrated rate law that does that. It's just a manipulation of the differential rate law to give you that information. It shows how the concentration of any given reactant or product depends on time, with time as a factor. Okay. So these are just summaries of what we covered so far. And this just says, because we try to minimize the effect of reverse reactions, we generally study reactions based on the disappearance of reactants rather than the appearance of products. If you can determine the differential rate law, that's all you need to do, because the integrated rate law can be derived from it. Or it may be easier to determine the integrated rate law, and then you can derive the differential rate law from that. And that's very often the case. And that I'm going to show you that in just a second. Now here's a reference, this second item. If you know the rate law for a reaction, it's easier to infer individual steps for a reaction. Most reactions do not occur in a single step. They usually, on the microscopic level, happen in multiple steps as part of a mechanism, a step-by-step mechanism. And if you know the rate law, the experimentally determined rate law, you can propose mechanisms. Nose is itching. What does that mean? No, ears itching, somebody's talking about you. Nose itching, you're going to have company, right? Okay. Let's see. Okay. This is called method of initial rates. And that just means that you determine initial rates for several different experiments. And the variable in those experiments from one to the other is concentrations. You change the concentrations of your reactant, and then you run the experiment and gather your data, concentrations and times. And then you change the concentrations in such a way that it changes some of those values, and you run the experiment again. And you do it several times, and it depends on the balanced equation as to how many of those experiments you need to perform to do the analysis afterwards. And that'll become obvious in just a minute when I show you an example. The main reason for doing multiple experiments is you want to conduct the experiment in such a way that if you have multiple reactants, especially, that you hold all reactants except for one constant for at least two reactions. So if you have A, B, and C, N, M, L. If you have that many reactants, then you want to do your experiments so you have rates where you hold this one, you let this one vary, right? It has Well, I'll just use some arbitrary numbers. Say we go from here from 1 to 2, but here you stay 1 and 1 and 1 and 1. So this is the only one that varies, right? And then you go back to 1 here and let that one vary, right? And then you go back this one and let that one vary. So then you have all possible combinations to where 2 of them are held constant for 2 different reactions. So this one would be held constant. These 2 would be constant from here to here, and then that one would vary. And for each one of those, you get a rate, right? Some value here. And that can be measured in terms of one of the reactants disappearing. And then I'll show you how to compare those in just a second. But that's the main idea. In order to do this type of analysis, you have to have 2 experiments in which only one of them varies. Okay. So another word before we move on about the order of the reactants. It's useful to understand not just the order of reactants, but the order of the reaction. It's bugging me. The order of the reaction is the sum of the individual orders. So if N were 1 and M were 2, then the overall order would be 3. It's just that simple. There's nothing magic about it. Okay, just to review, how do exponents, orders in a rate law compare to coefficients in a balanced equation? They're not related, at least not obviously related. Hold one second, I need to take this call. Yes. Yes, ma'am, I'll be there. Bye. Sorry, doctor's office. Okay. We have to talk about reaction mechanisms in order to relate balanced equations to the overall. And I'll say more about that when we get to mechanisms. Okay. So we'll have to come back to initial rates. We actually need to talk about the 3 different types of most common reaction orders. The 0 order we'll start with. Okay, let's see, I'm still on. Yeah, everything's here. Slid a little bit. There we go. Okay, the 0 order. N equals 0. Okay, for that, the differential rate law would be simple. I mean, just like we wrote it before, rate equals some constant, concentration of our reactant to the 0 power. Okay, that's a 0 order reaction. And notice from math, any number raised to the 0 power is 1. So that term actually disappears. And that becomes K, right? So what does that say? That means the rate is independent of the reactant concentration. It doesn't matter where you start, the rate's going to be the same. So what does that mean in terms? Well, first, before we go that way, let's look at the integrated rate law. Right. So we take, we take this information and we use calculus and we integrate the law, and we end up with this one. I'll put it this way. So the integrated rate law will then be the concentration of A is equal to negative K times time, and that K is the same K as this K, plus the initial concentration. Right? That's what that little zero down here at the bottom, that's your time zero. That's when you start. So that concentration, and this is the ending concentration over here. So notice we have the time is factored out so that we can know something about the time. What else do we see in an integrated rate law like that? For zero order, yeah, let me get one that works. That's a straight line. Let me get my head out of the way. That's a straight line. Y equals mx plus b. There's your y. There's your m, a negative k. There's your t, which is the x value. And there's your y-intercept. So if you graph it, let me get rid of that so I can put the graph down here. So if you graph it with t on this axis and the concentration of A on this axis, what do you get? Well, a negative K is a negative slope. So it has to go this way. And the slope is negative K. It also intersects right here at A0. So there's your y-intercept at A0. So what does that tell you? If we plot the concentration of A over time, right? We're measuring A like we did in that first table. We measure that and we plot A against time. With a zero order, you get a straight line with the raw data, just the plain numbers. All right. Okay, one other thing we can deduce from this, and the first time I was introduced to it had to do with radioactive decay. It's called the half-life. Well, you don't have to be radioactive to have a half-life. A half-life is just a mathematical expression that says, how long does it take for half of the original amount to disappear? Right? Well, there's your slope, right? Just like I drew on the board. Right here. That's the rate of A over time equals negative K is the slope. So you can, from the integrated rate plot, you can derive the differential equation because you have the K value. And if the raw data plots a straight line like this, then you know it's zero order. And you know, you know the n value is 0, right? Based on plotting the data and getting a straight line. That's all there is to it. If you get a straight line from plotting the raw data, then you know it's a 0 order for that reactant. All right, here's the half-life. So the half-life for this reaction, T 1/2, is equal to the initial concentration of A divided by 2K. Okay, so, and that K is the same K as up here, here, and here. So what do we know from that? We know that the half-life depends on where you start. Now the rate doesn't depend. It doesn't depend on the concentration, but the half-life does. Depends on where you start. So if you start at 2 molarity, right, you'll get a certain, well, that'll be the reciprocal of 1 over K, 1 over K. If you start at 1, it'll be the reciprocal of 2 times K. So the half-life does depend upon the concentration. It also depends on the K. The inverse of the K, actually. Okay, so what's next? First order, right? So a first order reaction N equals 1, we would have the rate equals K, and of course this will be a different K than that one, times the concentration to the first power. And you don't have to write that 1 up there, right? If you write the 0, then it disappears. But writing the 1 is redundant. I just write it for illustration purposes. If you've got A there and it stays there, there's got to be at least one of them. So the power would be 1. Okay, and that's the differential rate law. Now the integrated rate law is a transform. In other words, you take the raw data, the concentrations, and take the natural log of those values and plot them. And this is what you get. The natural log of A is equal to negative KT plus, the natural log of A 0. Right? So there's another straight line right there. If we plotted that one against time, then you would have to plot natural log of A. And you would get a straight line with a slope of negative K. Now what if we plotted that data, the raw data, right? Just plot the raw data like that for a first order reaction. You get a curve, right? So if you get a curve from plotting the raw data, you know it's not a 0 order. Because if it were, it would be a straight line. But if you plot the log, the natural log of A, and all your calculators have a key on them, ln, for natural log. It's not the log, it's the ln. 2 different types of logs. Then if you plot the natural log of A against time, you get this straight line. If that happens, then you know that it's first order for that reactant. And half-life. Okay, half-life then, well, after you plot it, of course. The half-life is T 1/2 equals 0.693 divided by K. So what we notice about this is the half-life, it doesn't matter where you start. It does not depend upon the concentration. right? The rate does depend upon the concentration, right, to the first order. But the half-life does not. It still depends upon K, but it doesn't depend upon the initial concentration. Okay. Look, maybe I've got enough room. Let me see if I got enough room over here to do n equals 1. So n equals 1 is our next and last. We're going to do 0 order, first order. Oh, sorry. I already did n equals 1, didn't I? N equals 2. There you go. Second order. We'll come back to this problem. I want to progress 0, 1, and 2, and then we'll come back to this slide. Okay, second order. The expression would be rate equals K to the second power. Now, if we plot the raw data for this one, you'll also get a curve. Right? But if you plot the reciprocal of the concentrations, you get a straight line. So there's the integrated rate law, and it's a positive slope, just K, T, plus the reciprocal of the initial concentration. Okay, and for this one, if you plot it, reciprocal, you get a straight line in that direction with a K slope. Okay, and of course down here, you get 1 over A to the 0. That's kind of small, and the video may blur that out. Okay, if you plot the raw data, of course, you get another curve. You just, like that. So what does that tell you? That tells you if you want to determine what is the order for your reactant A, do your transforms. Set up your time next to it, the raw data, raw concentrations, then the log transform, and then the reciprocal transform, and plot each 3 of those and see which one's the straight line. The straight line will tell you whether it's this one, or that one. And that's why proficiency with Excel is a plus in this type of operation, because I mean, once you put in your raw data with the time and the concentration, you can do very quickly transformations of values to natural log and to reciprocals, and then you can chart each one very quickly and find out what's your what rate law. Half-life for a second order reaction. The half-life then is 1 over K, like that. Okay, so in this case, the half-life for the second order is dependent upon the initial concentration. It's dependent upon K and the initial concentration. This one is dependent only on K, first order. 0 order is dependent upon K and the initial concentration. So the only thing that each of the half-lives have in common is they're all dependent upon K. And K, in each case, is in the denominator of the half-life. So they're dependent upon the reciprocal of K, actually. Okay. All right, so let me back up and look at that problem here. Okay. I'm gonna leave that up there until I have to erase it. And I've worked this slide has animations that progress through the reaction, so I won't have to write on the board. But let's look at the problem and analyze it logically, right? Word problems, like I've always said, they're meant to confuse. Especially, well, they're actually meant to confuse the test taker who doesn't know what they're doing. If you know the topic, then word problems are really no problem. You just need a methodology. So in this case, our first order reaction, look at that, they're giving you the order right off the bat. Our first order reaction is 35% complete at the end of 55 minutes. What's the value of K? What does 35% complete mean? Right? That means that 35% of the reactant has disappeared. Right? 100% complete would be all of the reactants gone. And it takes it 55 minutes to do that 35%. What's the value of K? All right, so here's the first step. First order reaction, we know this is the integrated rate law right here. Natural log of A equals minus KT plus the natural log of the initial concentration. All right, so now, since we know that the reaction is 35% complete, that gives us a ratio. So what's the remaining amount of A based on where you started? Right. The remaining amount of A, well, the concentration of A now, because 35% of it is gone, is 65%, or 0.65 of this ratio right here. Yeah, this ratio. This is the concentration now after 55 minutes. This is the initial concentration. And you've got 65% left, which is a ratio of 0.65. So how do you get there? Well, we use the integrated rate law. And we rearrange it. Notice the first thing we did. We moved this log term over here on the other side of the equal sign. So now it's negative. And that's equal to a negative KT. Well, the rules governing operations with log says that log of a number minus the log of another number is just the log of the quotient of the first one divided by the second one. That's a characteristic. That's a valid log operation. So this minus sign, when you put the logs together, becomes this divisor sign. And that's still equal to minus KT. So how do you get rid of the log here? Well, I'm going to have to erase some of this now, so I might as well do it all. Yeah, take a little time. But I'll show you a slide later, and it comes straight out of your book, and it's got all that information in one table. Okay, so how do we go from here to here? Well, it's based upon the definition of logs, right? So if you say, what is what is the log of A equals something, equals X. Doesn't matter really. Well, every log has a base, right? Common logs are base 10, powers of 10. The base for natural log is E. Right? It's one of those irrational numbers that pops up here and there. So this is the base, which means that A is actually equal to E to the X power. That's what the log means. So if we take E here, that's understood right there next to the ln, to the minus kt power, that's equal to this term right here. So that's the transformation that we imposed on this equation to get this ratio free of its log transformation. Now we know that this value, because of this relationship, that value is 0.65 after 55 minutes, that ratio. Because now the final concentration is 0.65 times what's left over. Why? Because 35% of it is gone. And this is what's left, 0.65. Okay, so that's what this term is for. Now, if you set that term, 0.65, equal to this E value, notice there's a K in there. We're after that K. That's what we want. So now we've got E to the minus K 55 power. How do you get at your K? Well, you reverse the process of the log transformation. You just take the log of both sides. Right? So if you take the log of this side and the log of that side, that's a valid mathematical operation. So the natural log of 0.65 is equal to the natural log of E to the minus K 55. And the log of a number to a power, if the number here is the same as the base of the log, then that log disappears and you're left with the power of E. Right? The log base E of E to a power is the power. So that's why we have minus K 55 over here equals to the log here. And then you just solve for K. And K turns out to be, after that transformation, 7.8 times 10 to the minus third reciprocal minutes. Now, the units of measure for K can vary all over the place. And that's because of that, you could have many terms, A, B, C, each one to its own power. And remember, when you have powers, you're not just taking the power of the number, you're taking the power of the units also. So if you take the power of all those units in the different powers, different orders of each of those units in those concentration terms, you can get some pretty complex units out of that equal to K. All right. So we went backwards. Now let's go forwards again and pick it up over here. Here we go. Let's see. Do I have this one worked out? I'm not sure if that's doing it or not. Let's just look at this problem. We've only been here an hour. I think I got time. Okay. So what's the problem? Here's the reaction. A equals products. And we're starting off at a concentration of 5.0 molar. All right. So let's extract information from that problem and put it on the board. Right? Word problems mess with your head. So let's extract the information and the questions and put them up here in a more recognizable form. So we have the initial the concentration of A with, and it varies with time, of course. So when we start, initial concentration of 5.0, what's the time? The time is 0 minutes. Right? It's just that simple. Now we're given the first 2 half-lives. So the first half-life is 25 minutes. So for the first 25 minutes, what happens to the concentration of A? It's cut in half. That's what that means, half-life. So after 25 minutes, you get 2.5 molar. Okay? What's the second half-life? The second half-life is 50 minutes. But what's your starting point? Half-lives always have to have a starting point, and you have a fresh starting point for each new half-life. So the half-life now is 50 minutes. So that's the difference between here and here is 50 minutes. So what does that make the overall time? 75 minutes, right? Right? This was 25. Oops. Minutes. This is T1/2 right here. And this is the actual time. Well, now what's the concentration? Well, this is our new starting point for this half-life. So it's 1/2 of that. Okay? Now we've got a complete data set. But it's in terms of half-lives. So a light bulb ought to go on, say, why don't we use the half-life formulas to determine the rate law? And the rate law, the value of K, and what's A after so many minutes, right? So how would you do that? Well, we look at the different half-lives, right? So if N equals 0, what's the half-life? It's 1 over, no, it's concentration of A over 2 K, right? I think I got that right. If it's N equals 1, then the half-life, T1/2, equals 0.693 over K. And then N equals 2, the half-life, is equal to 1 over K. I think that's right. Let me peek ahead. Yeah. Yeah, okay. All right. Oh, but by the way, this is, what's the starting concentration? What's the starting concentration? There you go. Okay, so what can we deduce? It'd be nice, right? We get these 3 choices. We don't know what the order is yet, right? If we could eliminate one of them, then that'd give us a better chance, 50-50, rather than 1/3. So what do we know? Well, is the half-life constant with initial concentration? The concentration here, you got this half-life. It's here, you got a different half-life, right? So that means N equals 1, it can't be first order because the half-life does not depend upon initial concentration for first order. And over here, it obviously does, right? So we can eliminate that one. So now we can choose between these two. So it becomes a little easier. So what we would do then is do the calculation for this one, inputting half-life, right, for this one, and pick an initial concentration. Well, we would do this one and find out what the K is. K is a constant. If K does not remain constant when we do those two calculations, for this one and for that one, then that's not it. The only one that works, the choice we have, is the one where we do the calculation of half-life for each of these two and find that K is the same for both of them. Right, so that's where we're headed. Right, so here we go. We've already eliminated first order. So if the rate law were zero order, using this, then we would do our calculation, right? See here, we put in 25 minutes, starting concentration of 5, and calculate K. K is 0.1. Then we do it again for the second half-life, 50 minutes, at a different starting concentration, 2.5. And we find that K is 0.025. That can't be it, because K is a constant. It cannot change. Well, as long as you don't change the temperature, right? So, just to confirm, by process of elimination, this reaction is second order, but we're going to prove it. Right? So we'll use the T1/2 for second order, do the calculations, and find out that both of them yield a K of 8 times 10 to the minus 3. Okay, so that answers our question. So there's your rate equals your K times A to the second power. And then K, insert the K there. Let's see, does that, oh, then we need to calculate what's the concentration after 525 minutes. Well, now we have K, right? We have the K. So we can plug it into the second order rate law here. There's your generic. And here we plug in the K, and we plug in the time, and we plug in the initial concentration, right? 5 after 525 minutes total, and then solve for the final concentration. And it turns out it's 0.23 molar. Okay? And there it is on one slide. So this is just to hammer that point home. How can you tell the difference among zero, first, and second order from their graphs? Well, let's see. Oh, okay. Next slide. Sorry. Well, you know, that really didn't answer the question. I've already told you what it is. I just thought it would show up on the slide. You plot, you do the transformations, right? You have, let's change this around. You have time, right? Then you have your raw concentrations of A, right, like that. Then you do the log transformation. You get a set of numbers, and then you do the reciprocal concentration, and you get a set of numbers. Then you plot this one, you plot these two, and you plot these two. 3 graphs. Whichever one is a straight line tells you the order. All right, that's it. Very simple. And the one that has a straight line, you can deduce from the integrated rate law what the K value is. Then you could write the differential rate law from the K, because you have both the order from the plot, that's straight line, plus you have a K from the slope of that line. Now, be careful of the sign. If it's this one, then K is equal to the value. If it's one of these, then you have to take the negative of the slope to give you the K. All right. So we've talked about single reactant reactions so far. What do you do if you have two reactants, right? And they're both going at the same time? Well, you have that initial rates procedure that I outlined before, but suppose there's another way. What if well, what would the rate law look like if it were a reactant A and a reactant B? Right, you would have the rate is equal to K times reactant A to its order and B to its order. Okay? So, if you only want to study A, because if you let both of them vary, then it's a mess. You can't figure it out. So what do? You increase the concentration of that one high enough so that initially it doesn't change. Not significantly. Right? There's plenty of it there, and depleting just a little bit of it to get the initial rates on this one will not change that one. Right? So what do you get then? Then you incorporate these two into a new K value. Right? It's a combination of those two, of these two right here. But you still got this one. Okay. Now you can study this one without worrying about that one. And that's what we do in the lab for the chemical kinetics. We have the blue dye and bleach together. And we study the disappearance of the blue dye spectrophotometrically. Right? We watch the absorbance units drop as the reaction proceeds. And then you go back and do the experiment again. Only this time, in our example, in our lab exercise, we take the concentration of B and drop it to half, decrease to half. It's still rather large concentration. So you're studying the rate in terms of this reaction again. And this K prime then is equal to the real K, like that. Okay, so a more complete discussion of that is in the method for that reaction. And there are a couple of supplemental documents that go along with it. So study those, preferably before you actually watch the video, and then the video will make a whole lot more sense. But that was just a teaser. That's what you do when you have two reactants. You increase the concentration of one of them so it's irrelevant. It doesn't change. All right. So here's that table I was talking about with the zero, first, and second order, and all the information that we covered right there. Right, so if it comes out blurry in the video, usually the slides are a lot clearer than my whiteboard. I don't know why. It just turns out that way. I think the initial recording, the Zoom recording, is a higher quality for the shared screen than it is for the speaker screen. All right. So let me erase this and make room. You know, I need to, let me get my hard copy so I can see where I'm headed. Here we go. Now, how far have we come? Actually, we've come a good ways. All right. Now this, you know, okay. Yeah. I was expecting something and I was about to jump the gun. Let's cover this one first. Say we have this reaction. A becomes products. And we start off with the same concentration as before, 5 molar. And now we got a different K. We don't have the same K as before. It's a different K. It's a different reaction, actually. Calculate the concentration of A after 30 seconds have passed if the reaction were 0 order for 1, first order, or second order. Right? So we're given initial concentration and the K and the time. And we want to see, well, what compare, you know, apples and apples. Compare 0 first and second order after 30 seconds. If it were 0 order, what would be the consequences? First order consequences, second order consequences. So if we do that calculation, like we did before, now we're going to use the 0 order equation, plug in our numbers, the K's, the T's, the initial concentration, and we find that we end up with 4.7 molar after 30 seconds. Okay, do it the same thing again for first order. The same data that we input, except a different equation because it's now first order. So if we do that for first order, we find that A concentration is 3.7 molar. So the only thing we did was change the order of the reaction. So for 0 order, we end up with this much. For first order, we end up with this much. It's like we're depleting A faster with a first order reaction than with a 0 order. So my guess is that for the second order, it'll even disappear faster than the first order. So we go over here and we say, okay, this is the integrated rate law for the first order. And we plug in the numbers for K, for T, for initial concentration, and find out, yep, the final concentration is 2 molar now for a second order equation. So the higher the order, everything else being equal, the higher the order, the faster the rate proceeds. Okay, so here's a sample, an example of an initial rates experiment. And actually, I took this one out of your review document. This is number 2 in your review document. So we're going to work this one in advance because my initial slide set didn't have an example worked out for initial rates. I said, that's crazy. I mean, the review document is just chock full of them. Well, what's my students going to do when they encounter one of these problems and never seen it before? So we're going to work one right now. All right, so here's the reaction. Right, the manganate ion is reacted with what? H2C2O4. Well, that could be that's oxalic acid. I mean, that neither here nor there for you guys, but I finally recognized it. If this were a 3 here instead of a 2, then it would be acetic acid. But this is oxalic acid. Never mind. Then hydrogen ion concentration. Right? Well, of course, you notice that the charges don't balance. This reaction is balanced. Take my word for it. But the charges don't balance. So what are we saying? This is probably a reaction that is this is a net reaction. We've removed the spectator ions because they don't matter. And if we have the spectator ions in there, the charges would balance. But this is the net reaction, and these are the reactants that we're interested in, and these are the products that come out. Right? So we're going to describe this reaction in actually several experiments with different initial rates. Right? So this is what the data looks like. Okay, that's a lot to digest in one viewing, but I'll explain it. So here we have the manganate ion initial concentration, the oxalic acid initial concentration, and the added acid, whatever that happens to be, the protons. And then here's the rate that was determined for each one of these experiments. So there are actually 4 different experiments. Okay. And this is the molar concentration of each one for this experiment. And that's the rate you get. So we changed the concentration. Notice from the first one to the second one, we only changed manganate. Right? The oxalic acid and the proton concentration stays the same. For the third one, we make these two equal. And let's see. For the third one, well, we've changed these two and kept this one constant. And then we changed the hydrogen ion concentration, and we keep these two where they were for the third one. Now, what does that mean? Well, if we, I don't know how I'm going to annotate this. Let me see if I can, rather than put it on the board. Let's see, text. Okay. So this would be Roman numeral 1. Yeah, that works. Okay. And this one is Roman numeral 2. Okay, and this one is Roman numeral 3. And this one is Roman numeral 4. Probably guessed that one already. Okay, so now we can talk about them in terms of which experiment we're dealing with. So if we want to know something about the change of the manganate ion, then we pick these first two, Roman numeral 1 and Roman numeral 2, because the oxalic acid and the protons are constant. They didn't change. Right? So let's write the overall reaction, because that's what we're aiming for. We want to know the overall rate law for this reaction. Right? So it would be rate is equal to the manganate ion to the n power and the oxalic acid to the m power, and then the hydrogen ions to the, I don't know, L power, I guess. Oh, what did I forget? Forgot my rate constant. All right. So, if we plug in the information, the beginning concentrations for each one of these, for the first Roman numeral 1, we would get let's see, Roman numeral 1, we would get rate equals K times MnO4 minus, oops, sorry. If we're going to plug in the values, we might as well do it, right? So that would be 1 times 10 to the minus 3. Now, 2, Roman numeral 1, concentration here, is 1 times 10 to the minus 3. The second one is 1 times 10 to the minus 3, and this is to the n power. That's to the m power. And this is 1 to the L power. Okay? Now, if we did that for Roman numeral 2, well, actually, what is the rate? We have a number there, don't we? 2 times 10 to the minus 4. There you go. Now, if we go back, if we do Roman numeral 2 experiment, what does its rate law look like? Well, it'll be a different initial rate, 8 times 10 to the minus 4 is equal to K. And then what's manganate now is 2 times 10 to the minus 3. But these are held constant. Right? They didn't change. Okay. Now, you're probably wondering, why did I write this one up here and that one down there? Because that one is bigger than this one. And my next operation, I want a whole number, not a fraction. So if we take this rate law and divide it by that rate law, what do you get? Well, look, that's equal to that, and they're all multiplied. So that divided by that is gone. This one, same. That one's gone. This one stays because that's different than that. But this is gone. Now all we have is this one. Actually, I don't need that. This one divided by this one is what? Well, 10 to the minus 4 divided into 10 to the minus 4 is 1. And 2 divided into 8 is 4, correct? So that term is 4, equal to what? Well, this term divided by this term, both to the n power. So this one divided by this one is what? 2, right? That goes out. 1 into 2 is 2. To what? To the n power. Correct? So 2 to what power is equal to 4? N is equal to 2. Okay, so now we know what n is. And we can plug it in right here. All right, we're going to do the same thing. Well, we may not take the time to do all the other two, but we would set it up the same way. So let's erase this one. Let's erase that. Let's erase this. Okay. And let's see. erase that, that, because they're all going to be in the same order. We just need to know, what are we going to put in there? Okay. So now what do we want to get at? Well, maybe we want to get at this one, right? So we need to find one where this one changes and these two are constant. Right? So where would that be? Well, let's see. If we go from 2 to 3, all right, Roman numeral 2 and 3, hold these two constant and those two constant, right? This one stays the same there, and this one stays the same there and there. Then that allows the middle one to change, right? So rather than put those terms in there, we know that with, actually let's put 3 on top, right? Why? Because this number is bigger than that number. Right? That gives us a whole number. So let's put 3 on top and 2 on the bottom. And now the rate for 3 is 1.6 times 10 to the minus 3. And the rate for 2 is 8 times 10 to the minus 4. Okay? There we go. K's are the same. These are constant, right? So they go out. These are constant. They don't change, so they go out. And now we just have this term in here, which is what? 2 on top, 1 on the bottom. Correct? So now we just resolve that. This is 2 to the m power. And this is, let's change that to minus 4, makes it 16, that's 2. Right? Check yourself. Divide this into that one, should be 2. Now m is equal to 1. Okay, so we can change this one then. There we go. That's 1. Now we don't have to write it. Right? We're just doing it to prove that we determined it was 1. Now, how do we get at the protons? Let's see, these are going to change. There. That's going to have number in it. Right? We want those two to cancel out, don't we? So which one gives us first and second terms, manganate and oxalic acid hold constant, but hydrogen ions change? Well, there's a 2, so this one has to be one of them. And where's the other one? Right? Well, we could do this one. These two right here. 4. Actually, 3 and 4, because these are the same numbers. So it doesn't matter. We'll put 3 on top and 4 on the bottom. 3 and 4. Right. So what do we have here? Well, they're both the same. 1.6 times 10 to the minus 3 and 1.6 times 10 to the minus 3. Right? And then value over here. Right? 1 on. Well, let's put 4 on top. Let's be consistent. 4 on top and 3 on the bottom. Means that 4 on top is 2 here and 1 there. Okay? So again, this one is equal to 1, right? And this one is equal to 2 to the L power, right? So what does L have to be to make that power 1? L has to be 0. So L is equal to 0. Okay? Everybody see how we did that? Okay, now that we've got those values, let's see, how would we write the rate law? When you write the rate law for a reaction, you always have the balanced equation upon which the reaction rate is based, right? So you will have the balanced equation, but when you write the rate law, well, we didn't determine K, did we? Let's see. So let's do that, and then we can write the rate law. So how would we do K? Well, we have any one of these experiments has a rate and concentrations that go with it and powers. So we could plug in those numbers and solve for K, couldn't we? We could just take the first one. So the rate for the first one is 2 times 10 to the minus 4. And then K is our unknown. And this one is 1 times 10 to the minus 3 squared. And this one is 1 times 10 to the minus 3 to the first power. And that one doesn't matter, right? Because anything to the 0 power is 1. So I shouldn't put an X, I should put it just 1. Right? So that concentration doesn't matter, no matter which one we use. Now we can solve that, right? So we keep K here, and we divide that one by this, and then divide it by that. And we get a K value. So that shouldn't take too long. So let's see. 2 exponent 4, change the sign, and then divide it by this one, and divide it by that one. And that means K, actually K is 200. K is equal to 200. Okay, now we can write our rate law. So the differential rate law is 200, if I did my calculations correctly. No, I didn't. Yeah, I always have to keep thinking. So I did that calculation wrong, right? I didn't square that number, right? So I got to do it again. And then we'll take this one, 1 exponent 3, change sign, and square it. Now I can divide. And then this one is first power, so I'm good there. So now K becomes 2 times 10 to the 5th power. Now we can write the rate law. So K then is 2 times 10 to the 5th. And then we have manganate squared and oxalic acid to the first power. That's it. You don't have that term in there because it's 0 order. And you don't have to write the 1 here. That one squared, there's your K. That's your differential rate law for that problem. Now you can go check number 2 in your review problems and see if I got it right. And if I didn't, you can hassle me about it. But I probably did because I caught that glaring error. Okay. Well, that's not the rate law, is it? No, it left out the K. Okay, so I've got some repair work to do there. Let me see. I just added this slide yesterday. That's a rookie error there. Let's see, I better write it down. K is 2 times 10 to the 5th. Okay, we'll fix that. All right. Now let's see where we're headed. I think my board is still on, starting to slide a little bit. There we go. Bring it back over. There we go. Okay. So, oh, I better erase those things. They tend to hang around. Where's my eraser? There it is. There, 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 and there. Okay. Let's go back to that one. That. Now we can talk about mechanisms. So what do we mean by a mechanism? A reaction mechanism is a series of steps that a reaction actually goes through between reactants to products. When we write the balanced equation up there, that's a before and after, not in between. In between, things are happening. Now, the thing about reaction mechanisms is that in the first place, it's an educated guess. Right? We think that based on the evidence, these are the steps that our reaction actually goes through to get to its destination, to products. So when a chemist is proposing reaction steps, lots of times they just shotgun it, just blast the pellets and see where they land. But the better chemist proposes different mechanisms, like this one versus that one versus that one. It could be a dozen of them. And then they go back in and say, all right, which one of these don't make any sense at all? Throw them out. Start paring them down. And it's that Sherlock Holmes thing. I don't know if I'll get the quote right. When all the evidence is considered, I'm not gonna get it wrong. Let me put it in my own words. How about that? When you consider all the possibilities and you eliminate everything that's absolutely impossible, then whatever's left, no matter how improbable, must be right. Now, of course, that wasn't Sherlock Holmes that said that. That was Arthur Conan Doyle using Sherlock Holmes as his mouthpiece. He was the author. Anyway, back to reaction mechanisms. So in the process of this step-by-step reaction, subsequent steps use products of the first step in their reaction. Now, they may pick up reactants that haven't been used yet from the original, but they use an intermediate, usually an intermediate from the first reaction to as reactants in the second or third or fourth or however many reactions. They call them elementary steps. Okay, so Here's a simple one, right? Nitrogen dioxide plus carbon monoxide yields nitrogen monoxide plus carbon dioxide. Right? So it looks like you just have one oxygen here, transfer over to that one to give you this one and that one. Okay, and these are the preponderance of evidence supports this mechanism, step 1, step 2. So here we have nitrogen dioxide. Nitrogen is blue and oxygen's red. So you have 2 of these, right? That yields a nitrogen trioxide and a nitrogen monoxide, right? That first reaction is just the simple transfer of one oxygen atom from one to the other. Then we take that nitrogen trioxide and react it with carbon monoxide. And we transfer that oxygen over to that carbon monoxide that regenerates a nitrogen dioxide and produces the carbon dioxide. Okay, so let's look at that reaction and say, okay, we started off with 2 nitrogen dioxides. So if the balanced equation only has 1 mole going in, right, 2 moles in this step, we've got to get that one out of there somehow. And that's what we do. If you take this step and add it together with this step, you should get the overall reaction. That's Hess's law. Remember, Hess's law. You can add equations together to get your target reaction. And then with Hess, of course, we were trying to determine the enthalpy of the reaction. But it's still, the same rules still apply, even with their elementary steps. They have to add up to the overall reaction. That's rule number 1. If they don't do that, and you've proposed it, throw it out. It's no good. Okay, so notice that when we add these 2 together, one of these nitrogen dioxides is in the reactants, and one is in the products. Those 2 cancel. So there you get your nitrogen dioxide back, and now overall you only have 1 mole of nitrogen dioxide in there. This nitrogen trioxide is an intermediate, and it's canceled here as a reactant, right? So those go out. So what do you have left? You have this one and that one, reactants, and this one and that one, products. Okay? All right. Now, it's instructive for chemists to identify what type of reaction the elementary step is. Does it involve only 1 reactant? Does it involve 2 reactants or 3 reactants? If there's only 1 reactant in the step, we call it unimolecular. And that elementary step then is first order, not because of the coefficients, but because we only have 1 reactant. Okay. 1 reactant means first order for that reactant in that elementary step. If there are 2 reactants, then for that elementary step, it's bimolecular, and that step is second order. Okay? If it's termolecular, that means 3 reactants, and the order for that step is third order. These are very, very rare. Think about it. If it's unimolecular, you got 1 molecule that does something. It rearranges or breaks apart. The probabilities of that happening are very high, right? It doesn't have to cooperate with anybody. It just, when it feels like it, bam. Bimolecular is a little harder to get together. you have two molecules. Let's see, over here. Two molecules coming together with sufficient energy, of course, and orientation. So if the bonds that are involved in the transformation are on this side of the molecules, then you may have a reaction. But if they come together, no matter how fast, and they're oriented improperly, no reaction. So the probability for a bimolecular is much lower. Termolecular, the probabilities of getting three molecules together with sufficient energy and the correct orientation to make the change is almost impossible. We only use termolecular elementary steps when there's no other choice. All right. That's also called the molecularity of the elementary step. Okay. So you've got these series of two or more elementary steps, and they never occur at the same rate. They're always different rates. So the slowest rate is the rate determining step. That is, nothing happens any faster than the slowest step. Why? Well, if intermediate products produced by one reaction are required for the next, then if this one's slower, then you can't move until you got a product from this one before you can go to the next step. It could be the first, it could be in the middle, it could be the last step. But the slowest step is the rate determining step. Now, that's good to know that, because if you know that, then the rate of the overall reaction is determined by that elementary step. And then you can work out the rate law from the elementary step and see if it coincides with the experimentally determined rate law that you did independent of this theoretical exercise. Since we can say something about the order of elementary steps, a rate law can be derived from elementary steps. And then you compare it to the experimentally determined one, and that's one way to confirm whether or not your mechanism is a valid one. Okay. I mentioned this rule first. You have to be able to sum up the elementary steps and get the overall balanced equation. If you can't do that, then that mechanism is invalid. Throw it out. And then the mechanism also must agree with the experimentally determined rate law. Just like I mentioned, the rate determining step, the slowest, use that to write your rate law and compare it to the experimentally determined rate law and see if they jive. So those two conditions have to be met in order for a reaction mechanism to be considered even remotely valid. Okay, so here's an example. We're going to decompose. Let's see, how am I doing? Just checking myself if I'm going to run out of time. Now, I think we're good. Decomposition of dinitrogen pentoxide. So here's the overall balanced equation. We know this is the reactant, unimolecular, at least in overall, and it produces nitrogen dioxide and oxygen in those proportions. So here's a proposed mechanism, 3 steps. And what we're saying is that this first step is very fast. You take 1 N2O5 and it has a forward and reverse rate, because it's really fast, of producing NO2 and NO3. So first thing you'll notice is there's only one of them, and there's no N2O5 anywhere else in the mechanism, right? So we're going to have to reconcile that. Then you get to the middle step, which is the slow step. So you take these two products and you make reactants out of them. Now they react and they produce these products, NO, O2, and NO2. That's the slow step. And then you take an NO3, right? We only produced one of them here, but we're using two of them, right? One there and one there. So we got to resolve that also. But you take an NO3, react it with an intermediate here, and produce NO2. Okay? So what do we have on the product side? Well, let's see. There's NO2, there's one there, and there's two there. So we need another one somewhere. Oh, excuse me. Yeah, we will need another one because this one was used up over here. So we are going to need another one over here. And oxygen. Well, oxygen's okay. Right? It's sitting right there. All right. So how do we do that? Well, these mechanism steps must add up to the overall. So we've got to see, can we do that? Well, the first step, if we multiply the whole thing through by 2, gives us 2 N2O5s and solves that problem. Right? Okay. And that means that now we have 2 of these that cancels that one and that one, NO3s. And that's good because NO3 occurs nowhere in the balanced equation. We got to get rid of that one. So if we multiply by 2 here, then that gets rid of this one and that one because they're on opposite sides of arrows. All right, what else does that do for us? Well, let's see. We can get rid of this NO2 and that NO2 because they're on opposite sides of the equation, right? They cancel. And these NOs cancel. So what does that mean? Well, now we've got 2 N2O5s right here, and we got 2 NO2s plus 2 NO2s down here. Now we got 4. That's good. And we've got O2 left. So the first condition is met, right? Add it all together, you get the balanced equation. Oh, I thought we were going to go further with that one. I guess we're not. We could have used the slow step here to derive an equation, a rate law, but we'll do that subsequent. Let's say we're going to use this one as sort of a generic. We have an A reacting with a B to make a C. Actually, 2 B's to make a C. This is our balanced overall equation. And the mechanism proposed is that A plus B yields D, an intermediate, and that's fast. And then we take the D and react with the other B, because there are 2 B's, right? And we make a C over here, right? So add them together, and you should get A plus 2B yields C. The slow step is the second one. So we can use that to write a rate law for the equation because the fast one doesn't count. The slow one is the only one that determines things. So yeah, it meets the first condition. Add it together, Hess's law, we're good. Now what? Well, let's take these 2 equations, right? And these K values are the rate constants for each of the reactions. In the case of the first fast equilibrium, we've got a K1 and a K minus 1. So this is the forward reaction, this is the reverse reaction, right? Using D as the reactant, K to the minus 1 would be set up as a rate law for the return reaction. Okay, and this one is a slow reaction, so we really only have one direction to go there. K2 is the constant there. So we have our Ks for each of these reactions: forward, reverse, forward. Now we'll take the slow step and write a rate law from it. So we have rate equals K2 times D, concentration, times B, concentration. And there's only one of them, so that's first order. And there's one B, that's first order. So now we are using balanced elementary step to write a rate law. We couldn't do that before because we had the overall reaction, and the overall reaction, you can't write a rate law from the overall reaction, but the elementary steps, you can, because of that concept of molecularity. So, are we good? No, because the rate law has to be in terms of the reactants, and D is nowhere in that equation. So we got to get rid of the D somehow. So that's what we do next. So there we are again. First we notice is that this fast equilibrium says that this rate forward is equal to the rate backwards. So we can write a rate law for this one, right? So there's K1 times AB, right? K1 times A, first order, and B, first order. That's the rate for the forward reaction. Well, it's equal to the rate for the reverse reaction, which is this one, K minus 1, times concentration of D, right? So those two are equal, forward and reverse. It's an equilibrium. And then we solve for D, right? So we get this term here derived from this equal to D. Now you know what I'm going to do. I'm going to substitute this term because it has reactants in it that we are familiar with and are part of the overall reaction. We're going to substitute that in there, the original, for D. So here we go. There, I've substituted. I took that rate K2 times D times B, and I substituted our D in here. Right? So now that gives us what? Well, that gives us this rate law, but in case you don't realize what I just did, this one and this one and this one are combined into a single K, right? They're all constants. So they become K times the rest of the equation, which is A times B squared. So the order of A is first order, the order of B is second order. And like I said before, let's go back. There's the equation. The coefficient for B is 2. And its order in this case is 2. That's coincidental. Right? It doesn't have to be that way. And they're not derived from one another. We derived this one from the elementary steps. Okay. So now, up to this time, we've been talking laws, rate laws. Right? We haven't said anything about why they occur. Well, I mentioned a little bit about why when I talked about collisions and orientation and all that, because that's the only way that I could explain it. But we need a bona fide theory with an accompanying model. In this case, the collision model, that will explain why these things happen the way they do. Okay, so here's the collision model. Molecules must collide to react. That sounds simplistic, but it's central to the collision model, right? If they don't collide, you don't get a reaction, right? If they're gases and they're like way over here, one's over there and one's over here, they're not going to react. They don't react remotely. They have to collide. And the factors governing whether or not a reaction will occur are, is there enough energy in the collision? We call that the activation energy, big E, little a, E sub a, which is dependent in most cases on the temperature of the reaction environment. Now, there are other things that can contribute, but for most chemists, temperature is it. If you increase the temperature, you increase the amount of energy available to the reaction. And proper orientation. They've got to be oriented correctly for bonds to break and reform however the reaction requires. So this energy that's overcome in order for a reaction to proceed is like holding a match and a piece of paper in the vicinity. Are you going to get a fire? No. You won't get a fire until you strike the match and touch it to the paper. What you've done when you strike the match is you've created enough energy for now the reaction of cellulose plus oxygen to produce products. You need that activation energy. All right, so here's what it looks like on a graph. This is the progress of the reaction on the x-axis right here. And this is potential energy. How much energy is going in, or how much energy is, doesn't even have to be potential, just how much energy is there. So you have a certain amount of energy that's possessed by the reactants, this reactant, and two of them are going to come together. So it's bimolecular. Oops, sorry. But if they come together now, they don't have enough energy. So the energy that they that is contained in their kinetics, right? They're smacking together. It converts them into a transition state. Sometimes we call that an activated complex, right? It's metastable is the word for it. It's not stable, really. It's metastable. It's unstable, right? The question is it going to roll down the hill to the right and make products, or is it going to roll back down the hill and give you reactants back, right? So you need this activation energy plus a smidge more to get it over the top of the hill. It's like a roller coaster. And that difference between where you started and the top of the hill is the activation energy, that distance right there on this graph. Now, the overall change in energy is the difference between where you started and where you end up, right? So if you started here and you end up over here, you get more energy back than you put in. So that's exothermic, right? If this line were up here, then it would be endothermic. Okay. So this is just stating the obvious. The collision has to have enough energy in it to exceed the activation energy, or get right at it and just a smidge more. And then you have to have the proper orientation. Right? That graph showed it. These two molecules come together, and if they're not oriented properly, they won't form these intermediate bonds. Those are not permanent bonds. They're only tenuous, temporary bonds. And then what ends up forming is this one becomes permanent and these two break, right? They're right here permanent. And right here, they're tenuous and that one's tenuous. And then as it rolls over the hill, this one becomes permanent and these break. So you get your bromine molecule here, the diatomic bromine, plus you have nitrogen monoxide, 2 moles of nitrogen monoxide. Okay, so this fellow, this smart mathematician, well, he was a researcher too, Arrhenius, I believe he was Swedish, said this is the relationship between the reaction rate constant and the activation energy of the reaction, right? And it varies with temperature, right? So there's temperature's a variable, activation energy can change, and of course the constant changes with temperature. Right? So it's only constant if the temperature doesn't change. So at this temperature, that's the K. Change the temperature, you get a different K. So naturally what you would do is you would conduct the experiment at 2 different temperatures, and in this case the focus is on activation energy. The activation energy for the reaction doesn't change. It's a constant. Under the conditions of the reaction, E sub A is a constant. But it's a constant variable. It's a variable compared to other reactions. So if we want to solve for this variable, we need to know the temperature. R is a constant, of course. That's a universal gas constant. And K is a constant for our reaction. So this is a little hard to deal with, this format. This is the differential equation. We need an integrated version. So this is what the integrated version looks like. And notice it has the form of a straight line. There's y, there's the slope m, there's your x, and there's your y-intercept b. Okay, so if you conduct this experiment over a temperature range, at least 2 different temperatures, but 3 or 4 or 5 would be better, then you can plot the inverse of the temperature against the log of the K that was determined at that temperature, and the slope of the line is equal to minus E sub A over R. Once you have the slope of the line, you can determine what E sub A is. Okay? So this is an example, what it would look like. Right? Plot those log Ks here against temperature, 1 over temperature, and the temperature, well, I shouldn't have to say this, but I will. The temperature must be in K, Kelvin units. But you take the reciprocal of the temperatures and plot them against the natural log of the Ks, and you get this line, and the slope then is equal to that value, which is E sub A minus E sub A over R. Okay, let's see how we're doing. Okay, we're good. We got 45 minutes. We have 42 minutes, actually. There's an interesting problem. I don't know if you've seen this in biology classes, A&P classes, any other science classes. There's a rule of thumb that scientists go by. And it's just that. It's not exact. It just helps you sort of ballpark the effect of temperature on reaction rates. And what it says is, for every 10 degrees, we say K here, but every 10 degrees Celsius increase in temperature, you double the rate of the reaction. Now, obviously, that's not true for every reaction. There's really only one type of reaction which that is exactly right. And that's the one where the activation energy is fixed at a certain point, because the temperature does govern the rates of reaction. And that is related to the activation energy for the reaction. So if you got a different activation energy, then that rule of thumb is not exactly doubling the reaction for every 10 degrees. So what I wanted to do in creating this next couple of slides is I wanted to find out what is the activation energy at which this rule of thumb is accurate. Well, there's a problem. You got to pick a temperature, because if you pick a different set of temperatures, you'll get a different activation energy. So I picked temperatures that were in a normal range, right? 25 to 35 degrees. 25 degrees is what we consider standard temperature for most reactions, except for gases, right? Standard temperature for gases is 0 degrees. But for everything else, reaction rates included, standard temperature is 25 degrees Celsius. So let's take that one and bump that one up 10 degrees, 25 to 35. There you go. Now let's see what happens. Okay, first we need to do is convert our temperatures to K. Right? So we do that for the first temperature here is 298, the second temperature is 308. Right? Then we take, and in fact, in this case, I'm going to use Arrhenius' original equation, simply because we're looking for a ratio. And we can do that ratio easier with Arrhenius' original equation than we can with the integrated version. So for the first one, this is what it would look like here. We're not going to plug the temperatures in yet. So this one has temperature 2, and the activation energy for the reaction is the unknown, actually, what we're looking for. And then we have this proportionality constant. E is a constant, right? It's that special number. And K for that temperature is designated K1. So we do the same thing for the K2. Right? For the different temperature, you have a different K. And here's your different temperature, here's your different K. Well, what we're saying is the reaction rate is going to double, right? So everything else being equal, that means that the K is going to double. So if we ratio, well, first of all, we're going to say that this K is actually twice the K1, the original temperature. So now we've got this equal to 2K and that one equal to K1. So if we ratio the two, K2 divided by K1 is equal to 2K1 over K1, right? Because that's what they're equal to. And then what are these equal to? Well, this one is equal to that, and this one's equal to that. So now we have an equation that we can solve, right? So these K's cancel out, it leaves you with 2. And these A's cancel out. Whoops, sorry. These K's cancel out. These constant A's cancel out. Now you're left with E of this term divided by E of that term. Well, as it turns out, if you've got the same base to different powers, then to combine them, you subtract the denominator power from the numerator power. So we say this one here minus this one makes it a plus because of that minus right there. So now minus and minus is a plus. So now we have 2 equals E to this power. All right, so we can factor out some things here, right? We can factor out minus E sub A over R, right? So we take minus E sub A over R out of here and minus E sub A over R out of here, and that leaves a minus behind, right? So that's why 1 over T2 minus 1 over T1, because we extracted a minus and left a minus behind. So now we've got this term that can be solved. So remember when we had E on one side, how do you get rid of it? You just take the log of both sides, the natural log of both sides, right? So there's the natural log of 2. And what we've done is, let me go back. The natural log of this one equals that power, because the natural log of E to a power is the power, right? So I actually skipped a step. And in the process, we have R on the bottom here, which I bring over to the other side. So that's why this one, this R is over here and not over here in the denominator. So now it's just a matter of solving the equation, plugging in the temperatures, right? Plugging in the gas constant and resolving. And it turns out, for that rule of thumb to be true, the activation energy has to be 52.9 kilojoules. If that's the case, then from 25 to 35, that rule of thumb is rock solid. And that's why you can go the other direction too, right? You can go cut the temperature in half, and the reaction rate is cut in half. Cut it in half again, or 10 more degrees, cut it in half again, 10 more degrees. So see that every time you decrease the temperature 10 degrees, you decrease the reaction rate halfway, right? So it's 1 over 2 to the power. And the power of 2 is how many times did you make that jump from 10 to 10 to 10, right? If you go from 25, and then to 15, and then to 5, and then to minus 5, and then to minus 15, you can see 1, 2, 3, 4, 5 jumps. So now the reaction rate is, the rate now is equal to the rate before times 1 over 2 to the 1, 2, 3, 4, 5th power. Okay? So you can see that if you get the temperature really cold, like household freezers are what? They're minus 20 degrees Fahrenheit. We'd have to figure that out. But if you had one, this would be easier. If you had one that was minus 40, then you'd have minus 40 Celsius. So it would be even further down here, another like 2 to the 6th or greater. So when you decrease the temperature that much, you cut the reaction rate by that factor. And that's why your food in a freezer stays fresh for a long time, because you decrease the reaction rates. No chemical, no biological, no biochemical reactions occur significantly at any rate that's significant. So they can stay months at those temperatures. And once you thaw them out, you can use them without fear of poisoning or off flavors or that type of thing. And that's why in my research, we used to take samples from, say, a greenhouse experiment. We take plant samples and we'd put them in a bag and immediately submerge them in liquid nitrogen. Liquid nitrogen is minus 195 degrees Celsius. So that virtually stops all chemical reactions instantly. And then we would, after they were frozen, we would store them at minus 100 degrees Celsius. We had freezers that were built that would maintain those temperatures continuously. And those samples would be good for analysis years. Okay. So now we'll talk about catalysts. And this is the last topic for today. We got a half hour to do it, so I think a half hour. Yeah, half hour. So we should have plenty of time. So what is a catalyst? And how do catalysts work? Right? How do they do their job? Well, first of all, what is their job? A catalyst is any substance that speeds up a reaction, but is not consumed by the reaction on the macroscopic scale. In other words, the overall reaction, you add a catalyst in this end, and it pops out of the reactants, unchanged, we think. Microscopically, it's intimately involved with the reactions. But macroscopically, the catalyst appears to be unchanged. That's the definition of a catalyst. How does it work? Well, like I just said, it is intimately involved, the catalyst, with the reaction. So what it does is it actually provides an alternate pathway for the reaction to occur. And that pathway, it actually occurs at a lower activation energy. Okay, so let's take a look at it. This is what the uncatalyzed reaction would look like, right, on our energy diagram. Take your reactants and you have to add enough energy to go from here to here. Let's annotate that. All right, if you went from here to here, that's your activation energy for the uncatalyzed reaction. But from here to here is the activation energy required for the catalyzed reaction. So at any given temperature, you got more than enough energy to drive your reactants over the hump. Now that in itself doesn't explain why the reaction goes faster. It's not a complete explanation. What we need is to know, well, if the reaction is going to proceed faster, then that means more of the reactant has to be converted over the same period of time. Right? So we need another graph to explain that. And before I do that, I probably ought to erase these two things. Okay. So this set of diagrams explains why more of the reactants actually go over the hump. This is a distribution, an energy distribution of the number of collisions. Right, so a very few, if almost zero collisions occur at this energy, which presumably is zero. And then once you get out here to the high energy level, there are very few of them that are high energy also. Most of them are in the middle somewhere, right? Under this curve. The area under that curve is a quantitative measure of how many collisions are occurring from one position to the next, from within an energy range. So if your activation energy is here, then you only have this many collisions that are available for the reaction to occur. But with a catalyst, you actually lower the activation energy like we showed on the previous diagram. And if you lower the activation energy at the same temperature and the same distribution of collisions, now more of the collisions under the curve meet the conditions of that new activation energy and will proceed to products. So that's why the reaction is faster. You have more collisions producing products. Okay, now we're going to classify catalysts. This is important for, especially for engineers, to know what's the environment. for the reaction. And if you're going to add a catalyst, what type of catalyst is it going to be? Well, some catalysts are heterogeneous. That is, the catalyst exists in a different phase from the reactant. A good example of that, the catalytic converter in your car. The phase for the catalyst is solid. These little ceramic beads, if you've ever poked a hole in an old catalytic converter and dumped the beads out, they're just ceramic beads that are coated with a very thin layer of platinum and palladium. It's usually an alloy, right? So that way you can sell them relatively inexpensive. If you had to use pure platinum or palladium, they'd be very expensive. So we just coat the ceramic beads, and that gives you lots of surface area for the reactions to occur. And that's what they do. The gases that pass through your tailpipe cross over these ceramic beads, and they attach themselves to the precious metal coating. And what that does is it brings them into closer proximity to other reactants so they can complete the or they just holds them steady in the right position so that they can break apart. So that's a heterogeneous catalyst. And this process where they attach to the surface is called adsorption with a D. Adsorption, not absorption. Absorption is what a sponge does when it soaks up water. Adsorption is what these gases do when they attach temporarily to the surface of the solid. And this is just steps that they undergo, right? First, they have to adsorb to the surface and become activated as single reactants or with their neighbors. And then they, actually, while they're on the surface, they migrate. Right? It allows them to move closer together. This is part of the elementary steps, the process of bringing them close together so that they're oriented properly. Then they react, and then the products desorb as they're released, and they travel on. The reactant, the catalyst is unchanged in this process, by definition, of course. So that's what it looks like. You have oxides of nitrogen that are produced in your engine. You have unburned hydrocarbons here, and you have carbon monoxide, which is an incomplete combustion product of any hydrocarbon. And as they pass over these coated ceramic beads, well, they say it's a mat here. I guess there's different engineering solutions to the problem. Originally, they were ceramic beads, but maybe a ceramic mat that's coated with the catalyst is more efficient. Oh, not only that, originally when the catalytic converters came out, people were just, they take a screwdriver, poke a hole, and empty the catalyst out of it, and then just patch the hole. And no one's the wiser until they started doing inspections. And they would see that people were, because the catalytic converter was robbing their engines of energy. It was producing back pressure, and the engines weren't running as efficiently. So you couldn't get the horsepower out of them that you wanted. So they just poke holes in their catalytic converter and open that up, and the gases would just fly right through. So maybe this was an answer to that problem. You convert from beads to a mesh, and that way when you poke a hole, nothing comes out. Okay, the other type of catalyst is the homogeneous catalyst. Right? The same condition applies. Catalyst goes in one end, comes out the other. presumably unchanged. But the homogeneous catalyst exists in the same phase as the reactants. Okay. Enzymes, for instance. Enzymes are catalysts, a type of catalyst that allow reactions to occur in your cells. And actually, they're more than just catalysts. They're control mechanisms, but that's another topic. But in some respects, they behave as catalysts, and they occur in the aqueous phase, in the environment of the cell. Now, this video I want to show you is a homogeneous catalyst at work. The decomposition of hydrogen peroxide will occur over time. Right? So if you put 3% hydrogen peroxide on your shelf in your medicine cabinet, you know, hot, humid bathrooms, eventually that hydrogen peroxide will be useless because it will have decomposed into water and oxygen. If you put it on your skin for a wound, in every cell there is an enzyme called Catalase. All cells have them. What they do, what Catalase does, is it takes peroxides that are formed as a side product of many reactions in the cells and can be damaging because they're very reactive molecules. The Catalase takes those undesirable peroxides, and decomposes them into water and oxygen. Now for chemists, and this occurs homogeneous, it's an enzyme, homogeneous catalyst. Chemists get at it a different way. You can decompose hydrogen peroxide by using a different type of catalyst. Potassium iodide. If you put that together with hydrogen peroxide, you'll get a rapid decomposition. It speeds up the reaction 1,000-fold, even more than that, actually. But how does it do it? Well, as it turns out, the iodide ion in there combines with the hydrogen peroxide in several steps. I think there are 4 steps that have been identified in that mechanism that cause the decomposition to occur very fast. So the slow step in the mechanism is orders of magnitude faster than the uncatalyzed reaction. So that's what this next video is about. You've probably seen something like this before. It's called elephant toothpaste. So this guy's going to add potassium iodide solution to, actually it's 30% or 35% hydrogen peroxide. It's 10 times as concentrated as that on your medicine cabinet, so it's dangerous. So here's what it looks like.
So that's the technique. Just dump it right in and see what happens.
Oh wow! Okay.
So we're releasing lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got, just dump it in really quick. Okay. Perfect. Yours is like more. And you just generate tons and tons of oxygen being trapped in so, okay? It's like a supersized version of what kind of happens when you pour time into your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything, if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff. What more?
Okay. That's a ooh-ah science. Okay, so this is the potassium iodide was in aqueous solution when they poured it in, and it combined with the hydrogen peroxide in the same phase. And it did so by this mechanism right here. We're not going to go through this mechanism. It's just to show you that the first step was the slow step. This iodide ion combines with hydrogen peroxide to produce this other intermediate and hydroxyls. And eventually you get down to the product, water and oxygen. And everything else cancels out except for the iodine. Well, the iodine does cancel too, but you put it in here and it comes out there. That shows you it's a catalyst. If it comes in one side and goes out the other, then you got a catalyst. Now, if it shows up as a product and disappears later, then it's an intermediate. There's a difference. An intermediate is something that you don't even know exists. And a catalyst is something that you actually add to the reaction and changes the activation energy of the overall reaction. Okay. Now there are other types of catalysts that are not so funny. And these are inadvertently produced catalysts. With the invention of the internal combustion engine, we produce these nitrogen oxides, right? Because air that's combined with the gasoline that goes into your engine is only 20% oxygen. You know, most of the rest of it is nitrogen, and it doesn't do anything except make undesirable compounds. And these nitrogen oxides float or mix and move into the upper atmosphere where the ozone is produced. Ozone is a product of oxygen being transformed by impinging ultraviolet radiation. And this ozone then even becomes a more potent absorber of ultraviolet radiation, much more than oxygen. But in the process of this movement of this nitrogen monoxide into the upper atmosphere, it reacts with ozone, and by this two-step process, decomposes the ozone back to oxygen. Right? And notice that it went in this side and it came out that side. That's a catalyst. It's a homogeneous catalyst in the gas phase. And now it's free to go do the same thing to some more ozone. So that catalyst, it just goes on and on and on. Just keeps creating ozone holes in the upper atmosphere. And that's bad because ozone is required to protect the lower levels and living tissues from damage from ultraviolet radiation. Okay. Fluorocarbons have a similar effect on the ozone. What happens is when these fluorocarbons migrate into the upper atmosphere, light converts them into adds the energy required to convert them into free radicals. Right? Remember what a free radical is. A free radical is any atom or compound that has an unpaired electron. In this case, it's chlorine. Okay? If we write the Lewis dot structure for chlorine, we have right? And there is your free electron, unpaired electron that is very reactive. Right? That's why two chlorines usually bond together. I mean, if you have pure chlorine in a container, it's always diatomic because the other chlorine is also reactive, right? And they form a bond, right? But in the upper atmosphere, we're producing a free radical chlorine, and what it does, it goes in and attacks ozone through this mechanism. That makes chlorine a catalyst. Chlorine in, chlorine out, and attacks the ozone and produces oxygen as a product. Okay. Now, the most notorious of all of these is Freon 12. It was the original chlorofluorocarbon that was used in refrigeration units primarily. Now we have compounds that are less likely to decompose in this fashion and produce those free radicals. But they're all fluorocarbons of some kind. Chlorofluorocarbons, hydrogen chlorofluorocarbons, there's a whole host of them. And obviously, they're more expensive than the original. Okay, so that's the last slide for that one, and I'll stop the share and see if anybody has any issues. We got 10 more minutes if you need it. Let's see. Oh, so I'll be back at noon on the CHEM104 Zoom connection. Just go into Blackboard and you can connect there if you need me. I'll be there for about an hour as usual. Okay, so what's on the agenda? That's the only topic, the only chapter that's going to be covered in the next exam. Right, so, yeah, where is it? Where's my... I put a lot of pages in this thing, didn't I? Okay, there it is. So that's today. Exam 1 on chapter 1011 and homework on 1011 due today. And we just covered chemical kinetics. Next Monday, we'll do a review. So we'll take that review document. So between now and then, you need to go in there and work those problems, as many as you can, and then bring the ones that give you trouble to me on the review day if you have to wait that long, or you can contact me in between. And we'll discuss kinetics in terms of those problems, because that's really the only way to learn chemistry, is to work lots of problems. You can get the theory pretty easily up front, but then to really understand it, you got to work problems with it. And then on the following Monday, we'll have exam on the kinetics and jump into chemical equilibrium and use what we understand of kinetics to help us with equilibrium.